Hi there my friend, it's Łukasz from Enterfea. Today I will tell you how to calculate critical bending moment using linear buckling analysis, sometimes called stability or linear bifurcation analysis. This is a really useful trick. If you are involved in structural design of any sort, you already know that most, if not all, codes require to calculate this value when you want to design beam due to bending. Critical bending moment is used to calculate slenderness, which is crucial when you design beam for lateral torsion buckling. Of course, you can calculate this value using one of many known equations. Unfortunately, those equations are actually based on many various assumptions, and in general practice it's sometimes hard to actually fulfill all the criteria. If you are interested, you can read about all the criteria in this post. If you are watching this video on YouTube or any other platform, there should be a link somewhere that will lead you to my blog. If you happen to design a beam that does not meet at least one of those criteria, for instance, is not symmetric into planes, then using those equations get a bit tricky since they don't take that into account usually. Of course, you could do differential equations and play with mathematics for a while to get the value you need, but in my experience it is far simpler to use the tools you already have in your solver. Nowadays, basically, regardless of the software you use, it will have a possibility to do linear buckling design, and this is all you need. So, just watch this video and learn how to calculate critical bending moment using numerical methods. One more thing. I want to use this occasion to tell you that I have created a free finite element analysis course for all of my subscribers. If you are interested in finite element analysis and want to learn more about it, you can get the access to the course following the link below this video. But now let's get back to today's topic. I will use an RFM program developed in Global. Firstly, let's create a simple beam. I will use IP 180 cross-section, and I wish my beam to be 10 meters long and pinned on both ends. Note that the default hinge support in RFM is actually rotationally restrained in Z direction. I wish my support to be restrained in rotational direction Y, which will prohibit the beam from rotating around its own axis. I will now create a simple load case, and I will deactivate the self-weight so it is easier for us to see the outcome. I will use a member load of 1 kN per meter, and now we can solve a problem. Note that the bending moment is 12.5 kN. It is good to remember this value because I will use it later on. RFM as a software is organized in a way that uses additional modules to calculate various things. Now, I will use a model that calculates steel elements. In each software, you have to implement either effective lengths or effective length factors, and in almost all software, the default value is effective length factor of 1. Since we are using a simply supported beam, this assumption is correct, so I don't have to change anything here. And I can do the calculations. Software used one of the equations for calculating critical bending moment and obtained the outcome of 9.44. Since the equation was used, certain assumptions were made, and in details in Stability tab, I can actually influence those assumptions. For instance, I wish that the load will be applied exactly in shear center of cross-section. Since this obviously influenced the outcome, I have to recalculate the problem, and now we obtain the elastic critical moment equal to 10.36, and I will refer to this value as to theoretical value, as to obtained from equation. This is of course not a numerical design, because equations were used, and in order to calculate critical bending moment with the equation, I need to have a model which do not use beam elements, but rather plates or shells element. Normally that would mean that I have to start the geometry from the beginning, but RFM has a very nice tool, generate surface from members, and when I click it, it changed the beam to a set of plates. Also you can see here that in integrated tab, the web I just highlighted already know that there is line number 1 integrated with it, so I can be sure that when I apply the load to this line, the surface actually knows this is a part of the surface. When I hide the nodal support for a second, you will see markers here. Those show that mesh refinement was used, but I don't wish to use mesh refinement. I will rather change the general settings and set the mesh size to 2 centimeters and show the nodal supports once more. You need to know that RFM actually sees a difference between member load and line load, and since we don't have a member and previously I used member load, I have to delete it and use line load of the same value. I will apply this load to a certain line, as I assumed previously. Also, since we are using plate elements, now the support in this point only supports a very tiny fraction of cross-section. This will of course cause significant stress concentration, so in order to avoid that, I will use rigid beams at the end, simply to allow better stress distribution. This of course do not change the fact that the support is still a hinge. With everything done, we can perform a stability design. This is in additional model stability. The default values for eigenvalues, we can go with that, and the stability additional model actually does linear bifurcation analysis. If you are interested in how this works, I have a separate post about it in my blog. Please note that we obtained several critical load factors, and the lowest one, the first one, is 0.854. If you remember, the bending moment in a beam was 12.5. If we multiplied it with the factor we obtain, the value is 10.67, and the theoretical value, 10.36, was only 3% different. We could search for the difference in mesh refinements, perhaps simplicity of the support, but I think that in most cases accuracy of 3% in engineering practice is enough. And since we have the model, we can actually play with it for a bit. For instance, let's see what would happen then when instead of making a perfect hinge in the middle, we would only support the bottom flange without any sort of support on the top flange, which is a solution I often see in engineering. And sometimes designers do not take into account that such a support actually influences the critical bending moment, which in turn influences the general capacity of the beam due to bending. You can see now that currently the multiplier is 0.74 and it was 0.85 before, which means that the critical bending moment decreased more than 10% because we changed the support. Of course, to this problem you could use equation to solve it, but I think it is easy now to see that if you draw your own cross-section, whichever it is, and then you support it in whichever way it is actually supported and load it in whichever load you wish, and then perform the linear bifurcation analysis in RFM, that would be a stability additional model, you will obtain the critical factor for the loads. And if you know how big moment those loads cause in the beam, this moment multiplied with the critical multiplier, this eigenvector value, actually gives the critical bending moment. And I used this method many times. I think it is useful and worth knowing of. I hope you will find this helpful. Thank you for watching. If you have any questions or remarks, leave them below in the comment section. And if you are interested in my free course, you can find the link leading to it below. Have a great day and see you next time.